Hello, and welcome to your statistics course. In this course, each slide is decorated with abstract art and other kinds of art as well. There's an explicit purpose for this, and it will become clear as we move forward. The objectives for Chapter 1. You will be able to answer the following questions. How can Picasso help you understand the purpose of statistics? What is the difference between a sample and a population? What are descriptive statistics? What are parameters? What are inferential statistics? And how can statistical methods help you in your work? This first painting is by Pablo Picasso. Notice how his images are mere suggestions of their objects: the bullfighter, and the horse. They're little more than simple ink blots, but we immediately know what they represent. The message here is that statisticians are like abstract artists in that we take a complex object and present it as an image with just enough information that people can easily infer what the image represents. There's no showy overkill or unnecessary busyness and detail. Statisticians, like abstract artists, present ideas in a clean and minimalist way. We'll revisit this theme in Chapter 3 when we see how abstraction helps us understand some other things about statistics. Here are 3 drawings by Picasso that reinforce the idea that we can represent a complex image with a simplified, stripped-down image. I've always been fascinated with Picasso's series of bull drawings. He started in the top row with a sketch including lots of detail and features of bulls. Then in the second row down, he eliminated some of the detail and drew a bull that is more representative of bulls in general, not one bull in particular. Finally, in the third row, with just a few brushstrokes, he captured the defining features and presented an abstract, idealized version of a bull, a stripped-down version of the original that conveys the idea of a bull with just a few simple brushstrokes. In our work in statistics, a description of a characteristic in the population is like the bull at the top, drawn with lots of detail and complexity. The bottom row is like a description of a characteristic in a sample, drawn with just the most important lines. This is what we want to do when we derive a set of statistics. We want to choose a simplified set of numbers that describe a sample, to make inferences about characteristics that exist in a larger population. So first, we need to understand the difference between a sample and a population. And in this slide, we will talk about the difference between a sample and a population. The population is the large group of people you want to know about, whereas the sample is the small group of people who will actually let you study them. You want the people in the sample to be a good representation of the people in the larger population. The way to do this is to make sure you have a truly random sample. That is, make sure everyone in the population has an equal chance of being selected into the sample. So it's important to begin the sampling process by procuring a list of all the people in the population, and then to use a random sampling method to select members of the sample. What are descriptive statistics? They are tools for summarizing the properties of an unwieldy amount of information from a sample. What are parameters? Parameters are numbers that describe characteristics of a population. So this is a bit of vocabulary. The two ideas are similar. The only difference is statistics pertain to a sample and parameters pertain to a population. Let's look at an example. When pollsters question a group of people prior to an election, they're trying to predict the outcome of the election. The people they poll are a sample, and they derive statistics to describe their votes. They're trying to predict the parameters of the population. In other words, they're trying to predict how the whole population will vote. Consider the following presidential polling and election results. 2 days before the election, a polling company identified a small sample of people and asked, "Who will you vote for?" Under the heading Poll, you can see candidate A was predicted winner with 47% of the vote. Candidate B garnered only 44% of the vote. 2 days later, the prediction came true. The election results are shown where candidate A won with 51% of the votes. Pollsters and statisticians had successfully predicted the winner. The last number in this row under the heading Difference shows the poll result was only 4 points lower than the actual result for candidate A and only 3 points higher than the actual for candidate B. Notice under the heading Poll is the phrase lowercase n equal 2,000. That means there were only 2,000 people in the sample. The lowercase n is the symbol statisticians use to stand for the sample size of the number of people in the sample. Under the heading Election, you can see the phrase uppercase N equal 100 million. Uppercase N is the symbol statisticians use to stand for the population size. Thus, there were 100 million people in the voting population. In sum, pollsters and statisticians tapped a sample of only 2,000 people to predict the behavior of a population consisting of 100 million people. It's pretty amazing, isn't it? What kind of magic did these pollsters and statisticians use to predict the future? Well, it wasn't magic at all. It was a rather straightforward scientific tool called probability sampling. The logic of sampling is driven by the laws of probability. In Chapter 9, you'll learn all about the laws of probability by thinking about the outcomes of games of chance, like the roll of a pair of dice or casino card games. Let's break down the process for computing summary statistics for a sample. We could list each person's name and who they voted for, but that would be inefficient. Most people don't want to read through 2,000 names and tally up the number of times each candidate got a vote. That's the job of the statistician, to count up the number of votes each candidate received and then to convert the number into a percent. Since 940 people chose candidate A, the statistician's job is to convert that number to a percent. 940 divided by the total sample size of 2,000 equals 0.47. Then we multiply by 100 to get 47%. It's simple. 47% is the statistic that summarizes the percent of people who chose candidate A. Candidate B received 44% of the vote. In the next section, we'll talk about using this statistic, 47%, to make an inference about the population. What are inferential statistics? Inferential statistics are tools that we can use to generalize characteristics of a smaller group, a sample, to a larger group, a population. When you read about polls in newspapers, you will often read something like the following. The margin of error for this poll is 4%, or the margin of error is 1%. The margin of error tells you how well we can infer the population value from the sample value. If the margin of error is 4%, that means we can be reasonably certain the poll result is within 4 percentage points of the actual election results. It gives you an idea how trustworthy the poll results are. If the margin of error is only 1%, the poll results are even more trustworthy. That is, we can be reasonably certain the poll result is within 1 percentage point of the actual election results. One way you can improve the trustworthiness of the poll results is to recruit a larger group of people for your sample. As the sample size gets larger, the margin of error gets smaller, and the poll results become more trustworthy. Margin of error is an inferential statistic. It gives us a way to make an inference about the population from the sample data. When polling data are reported in the news, the reporter will tell you the margin of error. For election results, the margin of error was 5%. That means the votes in the population were within 5 percentage points of the votes in the sample. In our example, the poll showed 47% chose candidate A. The margin of error for the population data was 5%, thus we can predict with reasonable certainty that the percent voting for candidate A in the actual election result will be within 5 percentage points of 47%. Recall, the actual election result showed 51% voted for candidate A, which is within the 5 percentage points of 47. Now, let's hold on a minute here. The phrase reasonably certain is a bit vague. Statisticians like to speak in more precise terms. Our statistical tools will allow us to nail down precisely what reasonably certain means, and we'll go into more detail about these secrets when we cover the mysteries of probability in Chapter 9. The second example hits closer to home. It has to do with a school district opinion poll, and it has a more practical use of statistics in your work. A few years ago, a school superintendent asked me to help him survey the employees in his district. He had about 2,000 employees, and he wanted their opinion on a new policy issue. We put together a questionnaire that people could fill out in about 30 minutes. He wanted to send the questionnaire to the entire population of employees, and I told him we could get virtually the same information by sending the questionnaire to a probability sample of only about 200 people. If you do the math, 30 minutes for all employees, 2,000, is 10 times larger than 30 minutes for 200 people. And keep in mind, he's paying people for the hours they work, and time spent filling out questionnaires is time taken away from instructional time. Well, I won't tell you what he chose, but I will say he spent a lot more money than he needed to. In the school district study, we found 1,740 employees approved of the new policy. So let's convert that number to a percent. 1,740 divided by 2,000 equal 0.87 times 100 equal 87%. 87% of the employees approved of the new policy. Is this a number that is a statistic or a parameter? Well, if you guessed that it is a parameter, you are correct, because the study assessed virtually all the employees, and this number 87% is considered a parameter, not a statistic. We don't need to do anything more with the number. We don't need to make an inference to the population because we've surveyed virtually everyone in the population. How can statistical methods help you in your work? Statistics allow you to summarize large sets of numbers or data quickly and efficiently. Statistics allow you to make statements about a large group, a population, based on data from a smaller group, which is a sample. And advanced statistics can help you understand causal relationships among variables. And we'll talk about causality in a more advanced course. Chapter 1, Key Points. Statistics are useful in your work because they save you time and money. It takes less time and money to gather information on a small sample than on a large population. A sample is a subset of a population. Statistics describe samples and parameters describe populations. Sample statistics allow you to make reasonable predictions or inferences about population parameters. In Chapter 1, we learned statistics can save us time and money. In Chapter 2, we'll learn about variables and measurement scales. If you are taking this course as a series of mini-courses, this lesson marks the beginning of mini-course number 1, in which we're covering the purpose of statistics and descriptive methods in chapters 1 through 5. After this mini-course, you may want to take mini-course 2, which covers the normal distribution, standard scores, and the bivariate normal distribution. And that will be covered in chapters 6 and 7. Then you may want to take mini-course 3. This mini-course covers regression, prediction, probability, sampling, and interval estimation. And these topics are covered in chapters 8 through 10. The next mini-course is number 4, in which we'll be talking about Introduction to Hypothesis Testing, and that's chapter 11. Finally, mini-course 5 is really packed full of lots of topics: estimation issues, the t-distribution, degrees of freedom, t-tables, statistics for categorical dependent variables, and inferences about correlation coefficients. And these topics are covered in chapters 12 through 14.